Hello guys, today we're going to take a look at the basic of differential equations. So for the first one, we're going to take a look at this equation where P and Q are constant. So what I mean by why it is equal to just a second derivative. So how to solve this kind of stuff is that we just guess the solution. Like there's a theorem over here which stated that the solution of this kind of equation has a form of yx is equal to c1 y1 x plus y2 x, where y1 x divided by y2 is not equal to a constant. Or we can say they're not linearly dependent. What I mean by linearly dependent is that if you divide y1 by 1, 2, you can get a constant. Yes. So now, for this kind of equation, we guess the solution that it has a form of a, e, r, t. A is a constant, and this is, And if we plug in, and we can see that it is basically r squared a e r t plus p r e r t a plus q a e r t is equal to 0. So when we cancel this term, and this term, we have the form of r squared plus pr plus q is equal to 0. So by solving the quadratic equation, we can get this is equal to negative p plus minus p squared minus 4q and divide by 2. Divide by 2. So we have this 1, 2. And now the solution we have now is yx is equal to a1 r1t and plus a2e r2t, where r1 is the case of positive and the case of negative. And now we're going to discuss another stuff. Is that sometimes this term can be smaller than 0. So what should I do with this? Is that we guess another stuff that we can represent it as a complex, in the complex form. So we can have something like this: alpha plus beta I, and the second root is equal to alpha minus beta I. This part is alpha, and this part is beta. Now, if we plug in, and we can see that the terms are y1 and c1 y1 is equal to c1. Oh, never mind. We change it to a1 for this one. C1 e alpha plus beta I and plus c2 e alpha minus beta I. And you can search it up if you want. So there's a formula for this kind of stuff, which is e, and this one is cosine plus sine. If you want to prove this theorem, you just can't use Taylor expansion for ex or ez, because it's a complex number. It's equal to 1 plus x squared divided by 2 plus x raised 3, and so on. You can see that this term is equal to sine x times I and plus cosine. And there's a really useful like application for this one. So if we get a form of this, we can like just draw in the complex plane where it has like radius of this. We can describe this point as this, and we'll talk about it in like 2 months maybe, yeah. And now we can separate the terms to C1, and this one is E alpha and times E I beta plus C2 E alpha E minus I beta. And this one, there's also C2 plus Y2. Now let me erase this part. Here we go. And through some combination by just changing the variables, we can see that like if we choose y1 is equal to this, this is equal to e alpha x cosine beta x. Oh wait, I need to tell you guys about something. So e I beta is equal to cosine beta plus I sine beta, and e minus I beta is equal to cosine beta minus I sine beta. And for this case, we ignore the like C1 and C2 for now. Just cancel. Just ignore it for now. So this stuff is equal to y1 and this stuff is equal to y2. And now we have this. And 1 divided by 2i and y1 minus y2 is equal to this. And now we can see that this is a solution for the like for this equation, and this is also the solution for this equation, because if you just plug in like if we choose this term first and plug in, we can see that 1 2 y1 y2 1 half plus p 1 2 1 1 plus y2 plus q y1 plus y2. For the term of y1, we know that it is a solution, so we can cancel this term out. And for the y2 term, this also satisfies the equation. Also satisfies the equation above. So the like combination of these two terms is also a solution for this above equation. And now we can see that the first solution, y1, just let me write it out again. y2. And the general solution now is equal to e alpha x c1 cosine beta plus c2 sine beta x. Okay, and if like the quadratic equation over here, so if p squared minus 4q is equal to 0, we only have one r now. So the mathematician came out with a solution of the form that c1 plus c2x er1x also satisfy this equation above. And if you plug in, you can see that. And now let's take a look at the example over here. So if we just plug in, you can see we're just solving for r for this one. which is equal to, like, factor it, R1 is equal to 3 and R2 is equal to -1. So the solution now is C1 E 3x and C2 E minus x. And also for C1 and C2, we need to get, how do I say this? So C1 and C2 depends on the initial condition of the function. So I'll talk about it later. So for this kind of problems, we're going to solve it like, we just divide it to that side. We can get cam x is equal to 0. And now for the solution, we can see that R is 0 plus minus and divided by 4km divided by 2 is equal to ikm. And for this kind of stuff, we have the solution of x is equal to a1 cosine kmt and a2 sine kmt. So if we give some like conditions, or just like if we choose this point to be like distance of a, and it is where it starts with velocity of 0, and if we take the derivative, we can see that if we plug in, we can get v is equal to dx dt a1 k m, and one is sine k and t, and plus a2 km cosine kmt. And for when t is equal to 0, this one is equal to a, and velocity is equal to 0. So plugging, we can see a2 is equal to 0 because cosine 0 is equal to 1 and sine 0 is equal to 0. So a2 is equal to 0, and if we plug into this equation, we can see that like a1 is equal to a. So the solution for x is equal to a and cosine kmt. So, and for this, we can visualize as, let me draw it, like a circle with radius of a, like it just turning and turning. Like for, it's just a projection to the x, and there's a y. And we can describe this point as a cosine kmt and a sine kmt. It just choosing the x component. So this one is turning with a constant angular velocity, and we'll talk about it in later. So you can, what I mean by constant angular velocity, it just means that the circle, the point is turning with constant velocity on the circle, just like this, constant. And now we're moving on to the second equation, which is dy dx plus px, y is equal to qx. And for convenient purposes, we first choose, we first consider a case where qx is equal to 0. So this is basically this. And if we move it to that side, we can get dy dx is equal to pxy, and we divide it here and move dx to that side, we can get the equation to be dy y is equal to px dx. And if we take the integral now, we can say this is equal to ln and from just y0 to y, and this one is whatever is equal to px, and plus a constant dx plus a constant. We just write it as this. If we take the we power it by e, we can see that this equation is equal to y is equal to y0 e negative px dx, and plus c, and we can move c to here, so this, or in other way we can separate it as px dx times ec. So this one is a constant, and we can treat it as time y0. This is also equal to a constant. We can call it c. This is equal to this. And now going back to this case, we also guess a solution. We also guess. So for the case of 0, this one is c. So we guess it might have the form of ax px dx, and when it might have the form of this. So if we plug into the equation, we get it to be a prime x e px dx and plus ax and times this, the derivative d dx e px dx is equal to chain rule, and we take the chain rules here, we can see that it is equal to, and d and times d px dx which is equal to px, and this stuff is a fundamental theorem of calculus, and times e px dx. So this term is equal to negative px dx and plus the rest of the term, which is, let me see, ax and times px, ax px, and this, which is equal to q. Let me erase this part. And now we can see that we move this to that side. We can see ax negative px. Oh wait, this term cancels out. One is negative and one is positive. We can see that they cancel each other out. So which leaves a prime x is equal to q x e px dx, because we move this to that side. And now if we take the integral of both sides, so the a dx moved to that side, we can see a is equal to the integral of q x e p x dx plus a constant, or in other way we integral from x0 to x, and this one is also x0 to x. So this one is a function of x, and we can treat this part as a constant. So for convenience purposes, we just treat it as a constant over here. And now, for the general solution, we can see that yx is equal to qx e px dx plus a constant, and times this x dx. Okay. Now we're going on and look at this trick. So this is basically like this one's acceleration. Acceleration is a double integral of x. So if we expand it out, we can write it as this. And this one is velocity. And by the chain rule, this is equal to this. And we can treat it, Vx, as a function of x. And this one is also velocity, which is equal to this. You can see they're equivalent. If we expand out, we can write it out. D square dv dv t, which is equal to dv dx dx dt. Oh my god, what I'm doing? This one's t. Never mind. Dv dx. So the first term is equal to, like, this term is just basically v. So you can see they're equivalent. And now we're going to take a look at a problem, which is kind of hard, or really hard. Just let me find that problem first. So here's Earth, and from its center, there's an object over here, which is distant of L, with the center, and the radius of Earth is R. And from physics, you might know that the force acting on the object is equal to g m. M is the mass of the Earth, and this one is the mass of the object, divided by the distance between them. So for this problem, we want to find the time it takes to reach the surface. So from physics knowledge, the acceleration mass times a is equal to the force acting upon it. So this is going to be this y squared. And dy dt squared is equal to g and y squared. And now, if you know, on the surface of the Earth, we know that g is equal to g m r squared. So if we move it to that side, we can get this equation is going to be g r squared y squared. And the initial condition is that at L, or at t is equal to 0, the height is L, and the velocity is also going to be 0 because it's the initial condition. And we know that d squared or second derivative of y is going to be equal to, like, the stuff I wrote on the top for this. This is going to be d on half dx. And now we can oh my god, what I'm doing. Wait a second. dy, which is equal to gm y squared. And now we can move it y to that side. We get d 1/2 d squared is equal to gm y squared dy. And if we take the integral, we can see that 1/2 b squared is equal to gm, and this one, the treating as gm. So this term is basically leaving to be. Two g r squared y plus c1, and this is a constant. So this is basically from L to some y. We can treat it as constant over here. So now we have v squared or v is equal to the negative of r rg y minus l. If we plug in the initial condition, we can see that. Or whatever, just integral from this and to this, and this from this, and we can see that it is equal to this. And now we have dv dt, or in other case, yes, this is equal to this term. And if we move this to, let me see. Wait, I'm done. dy dt is equal to this. And move it to that side, we can get r 1y 1l is equal to dt. And for 0 to t, and this one is from the height to the radius of Earth. So if we integral, we can see that t is equal to r. This one is kind of hard to integral, so if you want to check, you can do this. You check it by yourself. And plug in the initial condition, this one is equal to 0. And plug in that y is equal to r, we can get this one is equal to l r 2g and l r minus r squared plus l r cosine this. Okay, we're done with this video.